So the topic of this talk is the characterization of multi-photon interference. And as the first thing, I'd like to give context for how one gets to this problem. So the beginning of the story is 2001, when the Milburn-Laflamme scheme was proposed. Was there shown then that single photons and passive linear optics components were enough to achieve universal quantum computation, modulo some adaptivity. Fast forward to 2011, and we have a very interesting development. Aronson and Arkhipov discussed the problem of boson sampling. And what they argue is that an even simpler photocounting experiment with given enough photon could already serve as a witness for a separation between classical and quantum information processing. It was both interesting, a reasonable intermediate goal between having nothing and a full-fledged photonic quantum computers. People then went on and tried to implement their own version of a boson sampler, giving this machine all sorts of fancy names. Here I've listed a few examples. The crucial detail is that in order to claim that this machine works as intended, we require interference between perfectly indistinguishable photons, which a realistic source can only partially provide. Which raised the very fair point of were this thing actually working as intended? Were they witnessing what we wanted them to witness? There are a few ways to attack this problem, and what we'll be focusing on is a characterization of the interference behavior of the particle used in this kind of experiment. So when only two photons are involved, the distinguishability problem has a very well-known solution with a classical interpretation. And Danilo did me the favor of introducing the problem very well. It relies on witnessing the HOM effect, Hong-Mandel effect. I take my two photons, I impinge them on a balancing splitter, and if the two photons are indistinguishable, then there is a forbidden coincidence configuration. Measuring how often I see this forbidden configuration directly tells me how often my photons were either distinguishable or indistinguishable. However, this method of characterizing distinguishability has shortcomings when applied to a state of more than two photons. And the reason is entirely classical. It's classical correlation. Knowing when photons A and B are equal, B and C are equal, or C and A are equal, is not enough to infer when photon A and B and C are equal all at the same time, at least without further knowledge on their internal state. On top of this, people also started to realize that in describing multi-photon interference, there was much more to take into account. State of multiple photon can exhibit something called internal geometric phases, and then this, on one side, complicates the description of the photocounting statistic they produce, and on the other, complicate the interpretation of multi-photon distinguishability in terms of probabilities. Interesting solution to the problem of multi-photon distinguishability was proposed in a work by Matthias Ponte and collaborator in 2022. The interferometer that's proposed for this measurement, which you can see here, consists of two layers of balanced beam splitter connected by some internal rewirings plus a controllable phase shifter in the topmost mode. We're then asked to monitor a very specific configuration, which is the one where all photons exit the interferometer from the same mode they went in. The structure of the interferometer is sparse enough so that this configuration can only ever be produced in two ways: through identity path that I highlight in red, and through a permutation path. The probability of observing this outcome will depend on the overlap between these two configurations, and thus on the overlap between the initial state and a permuted version of itself. Having access to the quantity partially solves our issues, because if you think in classical terms, yes, you have a solution. The only state that is symmetric and that is cyclic permutation is the one that has all equal internal state. But as said earlier, internal phases can force this quantity to be complex. We have trouble interpreting as a probability, and we're left wondering what we're really measuring. This path interference idea turns out to be a very interesting key to get at the bottom of the problem of distinguishability. I can pick a random interferometer and select an outcome that I'm interested in analyzing. One can work out how this outcome can be expressed as a coherent superposition of all the possible discrete mode swapping that could have produced it, weighted by some transition amplitude that depends on the details of the interferometer. The probability of observing our selected outcome will then depend on all the possible cross-path overlaps, and thus on all the possible overlaps between the state and a permuted version of itself. We get to a first important conclusion that in order to predict the behavior of an arbitrary partially distinguishable state, we need to know the average value of n factorial distinct observables, the mode permutation operators, the symmetries of our state. They're observable, so like the first natural question is, how can we measure them? And turns out we can, and without much effort. What we need to do is borrow the design of the cyclic interferometer, rewrite the permutation path so that it realizes the permutation we're interested in, and the same exact two-path interference mechanism will allow us direct access to the distinguishability coefficient that we want to measure. The next relevant question is this information somehow redundant? So the first thing that we can observe is that not only these setups allows us to access all the parameters of the path framework, but they also live in the same settings that this framework is supposed to predict. They are like simple, very simple photo counting experiments. So we can set up a very powerful equivalence relation between states. If two states share the same exact photo counting probabilities for all interferometers and for all outcomes, then they will do so for our measurement setup. And thus we'll be able to check if they have the same exact symmetries. If they share the same exact symmetries, then through the path overlap formulas, we can directly show that they will produce the same photo counting probabilities for all outcomes and for all interferometers. So these two states can legitimately be called photo counting equivalent. We thus have a very solid definition of a tomography procedure, a quorum of independent measurable quantities that allow us to predict the interference behavior of arbitrary, partially distinguishable and photon state. So we went on and tried to implement this procedure. For this purpose, we used one of the machines built by Quandela, which is called Arcturus. This machine is a fully automated boson sampling setup equipped with a 12-mode reconfigurable and universal photonic chip and time multiplex quantum dot single photon source that is able to produce up to 6 photons at reasonable rates. On top of that, this machine is cloud accessible. I'm not an experimentalist. The only thing we had to do is just instruct through a Python script the machine on the interferometer that we wanted to realize and the number of coincidence outcome that we wanted to record. So going in a bit more into details, these interferometers actually produce more than the outcome I covered in the first slide. They produce to the power n. It's not really important the number. We can divide them into classes based on parities and record the number of coincidence count that you get for each class. By normalizing the difference in count, we obtain a phase-dependent, there's a phase shifter here, phase-dependent fringe value. One can work out that this fringe value will behave as a sine function, that we can then fit, and this allows us to access the distinguishability parameter we want to measure. The amplitude of the oscillation will give the information on the modulus of this number and its position relative to the zero phase configuration information about this phase. Because again, recall this could technically be a complex quantity. We then get something that looks more or less like this. For 4 photons, there are 24 permutation, and these are the 24 fringes that we measured with the machine. One can then try to reorganize the data in a bit more pretty way by sorting the permutation by the number of photons they move. This gives us a full coherent picture of the distinguishability spectrum of this boson sampler. We can then try to draw some very basic observation. What we see, the first thing is what we measure, the red points, is very consistent with the pairwise pure model, which is what you can, what the orange reference bar are there for. The other thing is that we clearly see the effect of temporal demultiplexing, where, for example, photons 0 and 3, the farthest apart, show us the lowest pairwise distinguishability. We don't have a crazy precision yet, but we can ballpark the 4 photon effects to a respectable 0.8. And most importantly, we see no evidence of internal phase in the machine. This is very valuable information because, as I said before, gives us the hope that the noise that we're facing is incoherent and could possibly be corrected, but more on that later. Very cool development of this story is that this machine has been completely disassembled, shipped to Canada, and reassembled. What you see here is the very happy hardware team after the whole process has finished. And the change has been quite seamless on my side. I just have to rerun my Python script and I can still take more data. So in the last 2 minutes, I'd like to spend a few slides on explaining why this information can actually be relevant. And first thing that one can do is further analyze this noise spectrum, further analyze the distinguishability behavior, and try to pinpoint a distinction between what is coherent related to internal phases on similar behavior and what is incoherent. Turns out that we can, and under this incoherent conditions, one can recover a description that's fully explained in terms of classical correlation. We can pass from a coherent permutation description to a partition description of our distinguishability noise, where the behavior that we see is fully explained by a mixture of all the possible discrete distinguishability errors when one or more photon is found to be completely distinguishable from the others. Um, this description is quite valuable because it behaves very well under particle subtraction. One can pretty easily see in this framework that partial experiments where one or more photons are purposefully removed from the machine carry unaltered the noise information about the subset of this noise component. Here, I make an example with this blue set. What one can think about doing is actually carry on various partial experiment and then come up with some kind of probabilistic error cancellation procedure where I try to mix all my partial interference result and get something that resembles much more the statistic of my ideal state, perfectly indistinguishable. The crucial detail is that the weight to perform the optimal correction, which can be carried on as long as the noise is incoherent, can be extracted by the information that is given by a distinguishability tomography. I have 30 seconds left, so what I'd like to do is just sum up a bit. What we did was to discuss a quorum of observables to describe the distinguishability behavior of photons and explain how we can measure them. We then carried on for photon distinguishability tomography on Quandela's machine. And we also argued that this information is actually very valuable when you want to understand and correct distinguishability noise. Last thing, I'd like to thank Quandela for making this project possible. Thank the organization committee for having me here. Thank my colleagues. Thank you for surviving until the end. And I'm open to questions, if any.
Thanks for showing us those excellent devices. Any questions, comments? Yes.
Short question. So the source, is it the same source with the delay line, or it's separate sources?
Yeah, it's the same source with a machine. I think it's shown in the picture. The picture is from the article where this thing is explained a bit more in details. Should be here, yes. So yes, you have a single source, and then you have a spatial demultiplexer that sequentially routes the photon in 6 different channels, and then you have a set of delay lines that whose purpose is to make so that the photons are all aligned when they enter the chip.
There's active switch in the demultiplexer?
What?
There's an active switch in the demultiplexer?
Yes, it's something under, yeah, they're developing various versions of this, but I think the one used for this machine used to be mechanical, if I'm not mistaken. But of course, the way to go here is to go to electro-optics because of speed and transmission.
All right, thanks. One more question.
So how intense is the computation to basically work out all of the permutation you need for n number of photons? Is that easy or
You mean how hard it is to go through all the procedure?
Yeah, because you have to work out what kind of you need to work out the whole permutation between 4 photons for this case, but
yes. So, well, first of all, it's a tomography procedure, so there's no way it's going to be efficient. Also, even for the natural state, you have to with the n-qubit state, you need to measure n to the power of 2 qubits. So this is more or less the photon equivalent of that, and the number of permutation is counted by the factorial. So, given n photons, I will have to perform n factorial experiment.
All right, thank you. So let's thank the speaker again.